Hi, my name is Tyler, and today I'll be discussing my deep learning project. The problem I have chosen to explore is predicting the future mortality rates of Australians using neural networks. Mortality data is a useful source of data that observes a variety of usages, particularly for government health and pension schemes, swift policy making in the case of concerning new trends, and appropriate risk calculation in the insurance space. To solve this prediction problem, I have found relevant data, tested the quality of different neural networks, and will further fine-tune these models to optimize prediction. For data, I have utilized the Human Mortality Database to extract male and female life tables for Australia, as it is a reliable data source that holds all my required information. As can be seen within the brief snapshot on the top right, I found this data source included 10,898 observations that spanned across the years 1921 to 2019 for Australians aged 0 to 110 plus. For the organising this data, I first reduced the age range to 0 to 99, as older ages had very few observations or no observations at all. I then transformed the mortality rates into log mortality rates for cleaner analysis. Then finally, I segmented the data into training, validation, and test sets into data sets including 5,800, 1,900, and 2,100 observations, respectively. Initial explorations of this data revealed that mortality saw a dip in childhood, followed by a sudden rise with adulthood and a gradual increase with age. Additionally, males have a higher mortality compared to females. For my deep learning approaches, I have chosen the architectures of convolutional neural networks, CNN, and gated recurrent units, GRU. CNNs are typically used for image-based classification problems, but can be redesigned to be utilized for time series. My current CNN contains convolutional, pooling, flattening, and fully connected neural layers. Unlike CNN, GRU models are more commonly used for time series data, and as such I have designed a simple model with one layer using 100 neurons and a linear output. Comparing these two models, it can be seen that CNNs are more complex in layering, but GRUs use a greater amount of parameters, as can be seen by 2.5 times more parameters in the images on the bottom left. Now that these models have been created, preliminary results can be ascertained to build an early understanding of each model's effectiveness. I included mean absolute error on top of mean squared error in case of any major outliers, although they both reveal similar trends. As can be seen by the noticeably lower scores, there is a greater prediction accuracy for CNN models compared to GRU. Additionally, the models are stronger at predicting female mortality compared to male mortality, most likely due to the greater variation for male mortality. I then briefly analyzed the loss curves of both models to observe minimized losses for GRU and CNN at 80 and 60 epochs respectively. An early stopping measure was built into the model to ensure overfitting did not occur despite the large number of epochs that I attempted. Next, I observed the comparison between the model predictions and actual log mortality. Across both males and females, CNN is far more accurate to the actual result, while GRU models consistently overestimate log mortality across all ages. It can be noted, though, that CNN does underestimate the mortality rates for females aged 15 to 25 and males aged 20 to 40. So key stakeholders may choose to use a different model to be more prudent. I then revisualized these comparisons through heat maps to observe many different test cases that were predicted. I observed similar effects of greater accuracy with CNNs and slight overestimations by GRUs across both females and males. Across all means of analysis, it appears that CNN has performed more effectively, but this result will continue to be investigated through further testing and hyperparameter tuning. Thank you for listening to my presentation.